So let's just quickly review from last time. Review from last time with an example. And I'm not going to number the example because I don't want it to interrupt our flow here into 2.4, or I don't want it to interrupt the indexing, the way I've enumerated the examples in 2.4. So let's say that we have a word problem. We're going to take a word problem and use a Venn diagram and the concepts that we talked about last time to solve some sort of problem based off of this data that we have that I'm going to give you here. So let's say 150 college freshmen were interviewed, 85 were registered for a math class, 70 were registered for an English class, and 50 were registered for both. Okay, so that's the data that we have. That's the data that we have here. So the question is, hang on one second, let me download the attendance report before I forget for our meeting today. Okay. Okay, the question is, or rather the first question is, how many signed up? Based off the data we have here, how many signed up only for a math class? Okay, let's get all the questions down and then we'll build the Venn diagram and then we'll answer the question. How many signed up only for an English class? And how many signed up for English or math? And the last question, how many signed up for neither English nor math? Okay, so that's a lot of writing there, a full page for me. So I'll give you a second to write these questions down. And then we will draw a Venn diagram to represent. So I'm not even going to attack any of these questions directly yet. I'm just going to draw a Venn diagram of this representing this set of data here. And then I'll go back and look at these questions and I should be able to answer them straight from my Venn diagram. I'll just have to interpret each one of these questions is asking about a different piece of the Venn diagram. And that's what I'll have to interpret. All right. Okay. So let's go to the Venn diagram. So I have 150 college freshmen were interviewed. So that's my universal set. So that's my universal set. I can label them up here. That's the universal set here. Oops. Yeah, U is the universal set there. I'll call the students who registered for a math class, I'll call that A. Students who registered for an English class, I'll call that B. And then how do I interpret this 50 were registered for both, well, that means they're in English and math. So that's A intersect B, right? That's A intersect B. If they're in both, that's what A intersect. Remember, we learned that operation of intersection last time. Okay. And really what I should have is little cardinality symbol bars around these, because these are the number of students in each set. Okay, so here we go. If I draw my Venn diagram, draw my rectangle, there's my universal set. So this whole thing is my universal set. And then here is A, and here is B. And we want to fill out this Venn diagram. Okay, so remember, the thing to do is to start from the center, from the intersection. We looked at a 3 Venn diagram, or rather a 3-set Venn diagram yesterday, or not yesterday, Monday. And in that one, we started from the very center intersection as well. And here, when it's just 2 sets, you still start from the intersection in the middle. So A intersect B, that's 50 right there. No problems with that. Okay. All right. So then how many students would live in this section of B over here? So I know there are 70 total in B, because B is the English class students. So there are 70 total in B, right? But 50 of them are stuffed over here. So that means there should be 20 over here. So that's my 70 elements in B. That's my 70 elements in B. 50 there and 20 there. And then there are 85 who registered for math, but 50 of them are already stuffed over here. This whole set here should be 85, but 50 of them are already there. So that means I must have 35 right there. All right, so no problems with that. Just some addition, subtraction, you know, depending on how you look at it, it's either an addition or a subtraction problem. Moreover, what can I say? What can I say here? The stuff that's organized in A and B, and then the intersection, and then out here, the students who are in math but not English, and the students who are in English but not math. All of that adds up to, what does that add up to? 105. 105. So if I was to write a number out here in this part of the universal set, right, out here, not in A or B, not in either of these, if I was to write some number out here to represent the number of students who are not taking English or math, or they're not taking either, then what number would I write out here? Does anyone have any ideas? You can speak up now if you have an idea.
45.
45.
Yeah, good, 45. So you guys got it. All right, good. 45 coming from the total universal set, but these have already been, these 105 students have already been organized in the sets A and B, so I'll take those away to find out how many are not in A or B, which is that 45 out there. So to make sure we're interpreting all these numbers right, in words, 50 students are taking math and English. Math and English. You know what, I should even write it out in words, just to emphasize it's and, not or, right? 50 students are taking math and English, that's that. All right, 35 students, how do I describe this chunk of A? 35 are taking, well, that's A is math, right? Are taking math, but not English. Another way to say that is 35 students are only taking math, or taking only math, 20 students are taking English. So this is the similar case over here. They're taking English, the set B is English class, but these 20 are taking English but not math. So those are the 20 students who are only taking English, not math. 45 students are taking neither. So they're taking other classes, are taking neither English nor math. And by the way, what about the numbers that I calculated over here? So I've got the 45. The 150 is just all the students who were interviewed. That's just my entire universal set. What about the 105? Does anyone have a guess as to how I could interpret that in terms of words? How could I interpret the 105?
Would it be the total of students that are taking classes?
But how can we say that in terms of, I'm looking for like English class and then or math class.
It would be 105 students
105
are taking
students
either
or-
math or English.
Yeah, I think you guys both said or, which is the kind of the point. Okay, so 105 students are taking English or math. English or math. That 105 is the union, right? A union B. All of them together, A union B. And remember that a union, if you interpret a union in words, the key word is or. They're either here or there, or in the intersection. Good. So now we've probably answered every single question that was posed back here. How many signed up only for a math class? So number 1 says how many signed up only for a math class. So I'll just put number 1 here and we'll answer it. How many students signed up only for a math class? Well, that would be this 35. They're taking math, but not English. They're taking only math. Okay. Number 2 said a similar thing. How many students signed up only for an English class? So that's going to be this case over here, the students who only signed up for English, that 20 there. So once you get the Venn diagram down and you know how to interpret it, the questions should just almost answer themselves just with your picture and your interpretation. How many signed up for English or math? English or math. Well, that means they can be here in the strictly only math club, here in the both club, or here in the strictly English club, because when I'm saying English or math, then they all count here, and we found that number to be 105. And then number 4 says, how many students are not in either club, right? How many students are not taking English or math? And we calculated that to be 45. Good. Okay. So a big point to make here is that you cannot necessarily answer these questions straight from the numbers that were given here. I mean, you can, but a picture is very helpful. And it would be incorrect to just kind of naively say, you know, oh, how many students signed up only for math, and then just to look at this 85 and say 85, right? That's incorrect. We just showed that's incorrect. It's only 35. So you really have to be careful here with a problem like this, where the sets are intersecting, where the sets are intersecting, and draw your picture and make sure you account for that splitting up of the sets. Some stuff being organized here and then here and there. We also did technically use the, where did we use it? The inclusion-exclusion principle for A union B. Did we? But we don't need to. Our picture got us around dealing with the inclusion-exclusion principle. All right, here comes another example. Now with 3. Okay. 3 Venn diagrams, or rather 3 sets. The whole thing is still just one Venn diagram. Let me see, what do I want to do here? Okay. let's go back to the example 1 that I think I was writing last time. This is actually from the text. The given Venn diagram contains the number of elements that belong to each set, that belong to the 3 sets. Wow, okay, spelled sets wrong. Sets A, B, and C. Okay, so why am I starting off saying this? Well, because we've seen Venn diagrams where the sets actually have the elements inside of them. Like there might be letters. Like I think the first thing we did was that one with the letters, right? With like the word pencil and education and whatever it was. And the distinct actual elements ended up in the picture. But often with these Venn diagrams, instead of putting the actual elements in there, you just put the number of elements in there. So they're represented by their cardinalities, not the actual elements. And that's very common. All right, so I'm gonna do my best here. So whenever you're drawing these 3 set Venn diagrams, you start with a set kind of skewed up to the top in the center, like that. And then you start with one, the next one is sort of skewed to the left. Wow, that's ugly. And then you have one skewed to the right. Okay. And just to make these numbers stand out, I'm gonna do them in red here. So very center is a 1. Now this picture, by the way, is on page 71 if you'd like to be able to see it in the text. The intersection there in that little spot is 8, and then we have a 5 there and a 10 there. So that's 5, 1, 8, and then 10 down there, and then a 26 left in the rest of A, a 22 in the rest of C, and a 19 in the rest of B. Find Okay, I'll give you a second to finish drawing it. And if you're having trouble drawing it and like getting the intersections to look right, then just make a note to yourself and say picture on page 71. But maybe you didn't have as hard of a time drawing it as I did. All right, so let's see what we're doing here. Okay, the first question says to find. So how do we interpret this? It says the cardinality, meaning the number of elements, in A intersect B intersect C. Now, we've done stuff like this before, but you've normally seen them like grouped with parentheses. But that's not happening here. And the reason that's not happening is because the order doesn't matter. When you've got a string of intersections or a string of unions, then you don't need parentheses because you can do them in whatever order. So that's a minor detail, but I just wanted you to know if you were worried because you didn't see the parentheses, it's because we don't need them because we're not mixing operations. We don't have intersections and unions, it's just intersections. So what they're saying here is find A intersect B. So the intersection of all 3, that's how you can interpret that. The intersection of all 3, and that would be the very, very center, the stuff that is common in A, B, and C. The cardinality, well, there's just a 1 there. So A intersect B intersect C is coming straight from the Venn diagram, just a 1. Just a 1. All right, so straightforward, right? What about find the cardinality of A intersect B? Okay, anybody have any guesses as to what this would be? Oh, yeah, go ahead. Yusuf.
Is it gonna be 26, 5, 1, and 8? Oh, I'm sorry, A and B. So 26, 5, and
But it's A intersect B. So remember, intersect means that we're looking for the overlap between A and B.
so it's like the number between the two circles, right?
Yeah.
So it's just 5 and 1?
Right, so we would say A intersect B is 5 plus 1, 6.
Thank
you. Yeah. Okay, Kim, did you have a question or were you gonna answer?
I was going to answer.
Oh, okay. All right. I'll get you on the next one. So yeah, so the point I want to make about this is before we move on, because I do have this is actually part B is where the book stops, but I'm gonna add some more questions here because this is a nice picture. I want to keep using it. I want to talk about this A intersect B thing. Okay. So A intersect B as a picture is this little flower petal looking thing, this little oval there, that piece right there. And it's split into the 5 and the 1. Okay, so if you want the cardinality, you have to add both pieces. So whenever you see a Venn diagram that's already built like this, like we have here, it's already pulled apart, right? It's got the set A is split into 4 different locations. This, where the 26 is, that 5, the 1, and the 8. And similarly for B, each of these sets is split into 4 locations or 4 groups, right? Depending on whatever the sets are, whatever's going on with this problem. So they're all organized into 4 different locations. So when I start asking you for to put them back together again, you have to start adding up. This is like the reverse of the problem we had a second ago, where instead of giving you the picture already organized, I just gave you the raw data, and then you had to pull the data apart to make the picture. Okay, this will make more sense when I ask you another question here. Let's find, now, how about just the cardinality of A? The cardinality of A. So now I'm asking for all the elements in A. Oh, Kim, would you mind turning your camera off? I didn't realize this last time. Actually, I've never learned this until I checked last time. But whenever I record lecture, if someone else has their camera on, it records their camera too. And I looked it up, and Teams is trying to fix that, but for now, it's not fixed. So that's why if you guys go look in Canvas and look at the videos I've uploaded, they're not our Teams meetings recordings. They're pre-recorded videos that I've done for this class in the past for the same course. So if you were curious as to why that was it. So learning more about Teams every day. I should say learning more about the limitation of Teams more every day. Okay, so Kim, do you know the cardinality of A here, or have a guess for how we would find it?
We would add 26 plus 5 plus 1 plus 8.
Yep.
If I'm not mistaken, that comes out to 40.
That's right. That's how we do it. We take A, which has been split into 4 locations, and we add up all those pieces back together. And does it come out to 40? I believe so, because that would be 32. Yeah, so 40. 40. Okay, so let's do some more. What else can I say? Let's see. Let's find cardinality of C. And then let's find cardinality of A union C. Okay, so Alrish or Lama, I saw your hand up earlier. Do you have a answer for part D here, the cardinality of C?
Yes, you just have to like put like 1 plus 8 plus 10 plus 22.
Right, all the stuff that's in C. So I'll say, yep, that's 22 plus 8 plus 1 plus 10. Is it 40 again? Oh, wait.
41.
Okay, yeah, 41. Thank you. Good. Now, A union C, the cardinality of A union C, we should recall is all of the things in A or all of the things in C. And we don't want to double add the stuff that's intersected between them, the 1 and the 8. So when we find A union C, we could use our inclusion-exclusion principle on this, but I think with a picture, we really don't need to. We can just say, starting at A, so A union C is all the stuff in A or C. So both of these circles all combined. So that's going to be the 26, the 5, the 1, and the 8. That's just from A. And then what is C contributing? Also a 10 and a 22. But I'm not going to re-add the 1 and the 8 again. I don't want to double count those because they're already considered right here. And then, what is that? That's 30, 40, and then 46, 52. So I believe that's 72. And you guys can correct me if I'm wrong there, but I think that's right. Okay, so I could ask you like a lot more questions about this. I could ask several more different combinations, right? But hopefully you're getting the picture for how to navigate around a given Venn diagram with 3 sets and how to find the size of intersections, unions, an entire set, etc. Okay, now the hard part is looking at a word problem and building a Venn diagram. We did one of those a second ago with 2 sets. Let's do it with 3 sets. So fresh sheet of paper. Ooh, you know what I could do? I wonder if this is going to work. I'm actually pulling this problem from a website. It's easier to have someone else build these problems. If I came up with them on the fly, the numbers might not work right. So I'm going to post it in the chat so you have it there for reference. I'll also write it down quickly. So we'll call this, what was that, example 1? We'll call this example 2. So I'm deviating from the text now. Example 2. Not from text. Oh, Kim, did you have a question? Or is your hand might be up from earlier?
No, I don't have a question.
Okay, your hand is still up. That's why I asked. Just making sure. So 100 students were interviewed. 28 took, so it's a similar setting to the last problem, students taking classes. 28 took PE, 31 took biology, so abbreviating biology to BIO, that's fine. 42 took English, we'll just say ENG. Okay, now we're starting to get into the intersections of each of these sets. So now 9 took, where am I? Lost my place. PE and biology. 10 took PE and English. So I need every combination here. and 6 took biology and English. And finally, the 4 took all 3. Okay. And the question is, how many students took none of the 3 subjects? Well, actually, there's 3 questions. Let's come to the questions after we draw our picture, because I bet the picture, the questions will be very easy to answer once we have our picture. The hard part is getting the picture down. How big does my set need to be? Okay, there's my rectangle. There's my set U. I'm going to label each of these sets just with the name of the class, because why not? It'll be easy to, they're short names, so they'll fit in my picture, and that'll keep us organized. I'm going to put the PE one up top. PE, and then over here will be biology. And over here will be English. All right. Where's my report? So, oh, hang on 1 second. I need to plug in my laptop. This thing is a dinosaur, and if I don't keep it on life support, it will die very quickly. So let me give it some charge there. All right. Okay. So again, just like I said, well, I've said a few times, we want to start from the very center, So the very center is the intersection of all 3 of these sets. That's going to be the very last thing I wrote down. So I am going to be working backwards here. The 4 goes in the center. Now, does anyone want to venture a guess as to what goes here? In this spot here. That is the leftover bit of the intersection of PE and English. Let's see. Kevin, what would it be?
Is it 10?
It wouldn't be 10. Why not, though?
Because of the overall intersection, so it'd be 6.
Right. Overall, this is saying that this 10 took PE and English. That means this whole little oval piece is 10, but there's already a 4 there, so we have to say 6. Yeah, so that's one of the critical, tricky bits about this, is that when you're building the Venn diagram, we've got to remember what this means, where it is on the picture, and then how it's split apart, right? So a lot of different, interpreting this from words to intersection of sets to picture and etc. Okay, so Kevin, if we now know that the sum of them should be, 10, if 6 took biology and English, so now I'm looking here, biology and English, then the sum of this intersection should be 6. So what should go here?
2.
Yeah, good. You got it. All right. And then that means over here that this should be a 5. That should be a 5. That's the last little intersection of PE and biology. PE and biology, the intersection should be 9, but there's already 4 there, so I'm writing a 5. Okay, good. So that idea of adding them up and then taking the remainder and writing it down is going to continue into our next step when we say, if 28 took PE, that means the entire sum of this circle should be 28. So if I want to find this missing piece, I need to think about, okay, what's 5 plus 4 plus 6? And then subtract that from 28 to figure out what goes here.
13.
Good, 13. Okay, now what about, and let's see, it was Stephen, what would be left in English?
20.
I think so, yes. Wait.
No, that's biology. 20 is biology. I'm sorry.
Okay. Yeah, 20 over here, that's 6, 11. Yeah, so biology would, if biology adds up to 31.
English is 30.
Right, yeah, there we go. English is 30, there we go. Okay, so the point is that,
Sorry.
that's all right, that's all right. Okay, when you are doing one of these problems, and you will have to do one of these problems either on homework or on exam, the only number that gets explicitly written down from all of this data into your picture is that 4, right? That is the only number that explicitly got copied down. The rest of them, you have to do some arithmetic to find out what goes, in the rest of the positions. The nice thing is here, it's not hard arithmetic, right? We're not multiplying or dividing, we're just adding up numbers. So let me just reiterate this. So just with one of the sets, like if we were trying to find that 13, so if I said, where did the 13 come from? In the PE, where did 13 come from in PE? Just to make it very clear, the cardinality of the set PE should be 28, but we already have some of PE organized. Wow, why can't I spell today? Organized into groups inside the set PE. So if we want, and I'm going to draw a picture here to show what we want from PE. If this is PE and I have this and this, where this is a 5, a 4, and the 6. So if we want this location, call it X, we need the sum of all of these to be 28. X plus 5 plus 4 plus 6 equals 28, which then, of course, ends up yielding that X is 13. So that's another way to look at it there. You can build a little equation out of it. But the point is that they should all sum up to whatever the cardinality of the whole set is. So you have to deconstruct, you have to pull the set apart. Okay, that was just building the picture. What about the questions, the actual questions that were asked? I'll leave that there for a moment if you're writing it down. All right. So the actual questions were, how many students took none of the 3 subjects? Actually, we didn't explicitly write that down in our picture, but that's okay, we can find it. How many students took none of the subjects? Well, so we're looking for a number that would go out here in the universal set that is, so there are 100 students altogether in my rectangle, and a lot of them have been organized into here, you know, these locations here. I want to know if I subtract out all of these students who took, you know, PE, biology, or English, how many are left of those 100 students that were interviewed. So the way to do this is I take my universal set cardinality and I'm going to subtract every single one of these numbers. That's what I'm going to do here. I'm going to subtract the students who only took PE, which is 13. I'm going to subtract the 5 students who took PE and biology, but not English. I'm going to subtract the students who took PE and English, but not biology, which is 6. I'm going to subtract the 4, which is the intersection of all 3, so the 4 students who took all 3. I'm going to subtract the 2, which is the students that took biology and English, but not PE. And then I'm going to subtract the 20 students who took biology, but nothing else. and the 30 students who took English but nothing else. Essentially, once you have the picture down, you're just subtracting all of the numbers. These are all distinct now. It's safe to just subtract all of them to find out what's left outside of these sets. So the students who are not taking any of these classes. And that's going to give I really don't feel like doing that in my head, so I'm just going to pop it into the calculator. Minus 13, minus 5, minus that, minus 2, and that. All right, so I'm getting 20. That's how many students were interviewed but are not taking, so they're taking other classes, not PE, biology, or English. The next question is, Kevin, did you have a question, or I just want to make sure I'm not leaving anybody with a question?
Sorry, my
Okay.
hand was still up.
Okay, that's okay. Listen, it's not just you guys. I have department meetings and people do that all the time, leaving their hands up. It's not just you guys. It's fine. I just want to make sure I'm not leaving anybody with lingering questions. How many students took PE but not biology or English? So this is a good question. Asking you to interpret some spot on the picture. How many students took PE but not English or biology? Does anyone want to venture a guess as to what that would be based off of our picture? Yes, Arish?
13.
Yes, good. The 13. Good. So ideally, if you can take a data set that we were originally given, get a picture out of it, that's great. If you can then point at any number on this picture and tell me or tell yourself what it's representing, then that's extra great, right? That means you're really getting it. So if I pointed at this 13 and ask you to, what does it represent? That is the students who have taken PE, right? Clearly they're in the PE set, but they did not take biology because they're not in the biology circle, and they did not take English because they're not in the English circle. So they took PE, but not biology or English, which is exactly what the question asked. Next question is, how many students, this is a typo, okay, that's okay. How many students took biology and PE, and PE, but not English? I know other people have raised their hand and I haven't called on them, but I don't remember. I don't remember who. And I can't even see everyone. I just see like a few and then plus 14. So but let's see. How about, okay, fine. Go ahead. Arish.
Sorry, 5.
That's okay. Yes, I think so. 5. Yes. Let's see. How many students took biology and PE? All right, so that first part, biology and PE, tells me that I'm looking in this little intersection here. If they left it at that, if they said how many students took biology and PE, it would be this whole part, which would be 9. Which in fact was that we were given that up front. But they said took biology and PE, but not English. So I want to exclude the students who also took English, which means I'm just left with that 5 there. The students who took PE and biology, but not English. So good. All right. I'm going to leave it at that with this section. This section takes practice, but I'm going to leave it at that. And we'll talk a little bit about the next chapter and the next sections. Here are some problems to mark for review for section 2.4. 7, 11, 13, 15, and 17. So make sure you're practicing, especially with those word problems. And you can, obviously I've given you problems to practice here. There's also the practice function in Hawks. So if you're about to do the Hawks assignment for 2.4, you got to do the certify portion to get credit for the assignment. But you can do the practice one first just to make sure you've really got it if you want more practice with these word problems. But that is all I'm going to say about 2.4. And that finishes chapter 2. And now we're going to move into chapter 3. But before I start digging straight into chapter 3, just want to remind you about overall the motivation for chapter 2 was to learn the motivation for learning set theory. I'll put the objectives in the next sentence. The motivation for chapter 2. Why am I'm like having a brain fart? Let me sit back and think about what I want to say. Okay, was to learn how to organize elements in sets for the purpose of this is awful. I am not saying what I want to say here. Never mind. How about this? The objectives, for chapter 2 were to learn how to represent sets. So remember, we learned roster notation, which is putting them in a list, and set builder notation, which was different, right? How to represent sets, compare sets. So we learned the equivalence versus equal, and also we learned the subset versus proper subset thing. Compare sets, perform operations on sets. That was unions, complements, and intersections. Perform set operations, and to then apply this knowledge to real life problems. And I'll put real life problems in quotes. The real life problems we did are like those surveys, the word problems. But also, we're going to be using the set theory stuff in chapter 7 when we talk about probability. But so you should come out of chapter 2 feeling like you know how to write down and represent a set in 2 ways, set builder notation and roster notation, how to compare sets with equals, the equal sign, equivalent sign, subset, proper subset notation, perform set operations, so that's unions, intersections, and also complements, and to then apply all of that stuff to those word problems that we did, mainly applying the set operations to the real life problems. Okay. So if you come out of chapter 2 feeling like this makes sense, and you see what I'm getting at here, like generalizing chapter 2 and this makes sense to you, then that's good. The objectives for chapter 3, which is called logic, are to, so why are we learning about logic in a math class? And what's the point of it? How can I motivate you to learn about it? Learn to identify common errors that people make, errors in logic. To learn to identify common errors in logic. And to learn how to make strong arguments. Okay, so that's kind of vague, but I just want to give you a little idea about what we're going to do before we just get straight into it. And I'm not leaving myself a lot of time to get straight into it, but that's okay. All right, so chapter 3 is called logic. We're going to be looking at, in chapter 3, what a logic statement is in math and just in a broader scope, what a logic statement is. We're going to be looking at how we can build larger logic statements from compound words that we've already been looking at, like and or. And then it's kind of going to culminate in looking at the truth values of different logic statements and how connecting logic statements with different compound words leads to different values of truth. And that is all like, what does that mean? Well, if I step back and I said, what are we going to be doing? I would really just say this again. We're going to be learning how to identify common errors in logic that you have probably heard people make before. You've probably made them. I know I have. We're going to be looking at how to fix those errors in logic. And then also that'll sort of help you become like a better debater if you do debate with anyone, right? And more generally, just how to make stronger arguments. Maybe you're not debating, but just how to make stronger arguments in general. So that's vague. Let's just get straight into it so you can start to see what I'm talking about with section 3.1, which is logic statements and their negation or negations. Logic statements and their negations. Just gonna give you a definition to think about and then we'll end for today. So a logic statement, or just a statement, is a complete sentence that makes a claim. I'll say this is coming from the text, that asserts a claim that is either true or false. That a claim that is either true or false, but not both at the same time. Okay. So that doesn't seem like groundbreaking or anything, but let's make sure we understand this. So would it be a logic statement or just a statement if I said that the Return of the King, Lord of the Rings, The Return of the King is the best movie ever made? No, that's not a logic statement because it's an opinion, right? A logic statement would be like if I looked outside and I said, it is raining right now. Well, that's false, right? I can assign a value of truth, of false, to that statement. Okay, so pretty easy definition, but we'll do some practice with it next time, and then we'll look at the negation. This first section is going to be a lot of definitions. Could be a little boring, but we'll get through it next time, and then we'll also push into 3.2, and things will get a little bit more interesting there. So you guys are good to go for today. You can stick around if you have questions.